we might be interested in the area under the curve, okay? The area bounded by the curve, this axis here where I have t, the line A and the line x, where x is some value that's larger than A, but some arbitrary value that we can change. Now this is also defined using an integral. So we can say the definite integral, where our lower limit is A and upper limit is x, and we're going to integrate f of t, because f of t is our function here with respect to t. So we write dt. So again, this is the integral of f of t with respect to t, and the lower limit is a and the upper limit is x. What this defines is the area under the curve f of t, by this line a, by this line x, and bounded by this axis here, the t-axis. Okay, so it's all of this area here. Now I can also say I want a function. So let's say here I want some function that gives me the value. So I want the function to output the area between the line A and between the line X and here and the curve, and I want that to output the value of the area. So I want to be able to change the value of X and for the function to output the area. So I'm going to call that function a of x. So here you can see that I can change the value of x and get a different output. So it looks like if I was to increase the value of x, the area would increase, and if I was to decrease the value of x, then I should output some smaller value. Then the next thing I'm going to think about is I'm going to differentiate this. So I'm going to do that from first principles. So I have to apply the formula. We take the limit. So limit as h goes to 0. And I want to differentiate this. So that will be the function a with x plus h in there. So a x plus h, take away ax over h. So this is just applying the differentiation formula, the differentiating from first principles formula on the function a of x. Now here I'm going to just consider the numerator. So let me write that again. So if I have a of x plus h, take away a of x. Now I'm going to try and think about what this means on my graph here. So a of x here is the area here, and a of x plus h, so there must be some x plus h here where I'm adding some h to x, and it will be the area bounded by that line and the line a. And then if I was to subtract them, it will give me the area from wherever x plus h is to x. So let's draw x plus h here. So if I have x plus h, okay, so remember a of x plus h is the area from this blue line to this red dotted line. A of x is the area from this blue line to this blue dotted line, and if I subtract this from the first area, that would leave me with this bit here. So that would leave me with all of this here. Okay, so this is the area that I'm thinking about when I write this. Now the next thing I want to think about is, suppose we want to make h very small, like we do here. So we want to make h very small, and what you can see is when h is very small, so let's say, let me just show what I mean by the h. So this value here is h, and if I was to make it smaller, I'm going to bring it closer and closer to the x. Now let's make a new line here. So if I make a line here, so that's x plus h. If I go from my blue dotted line and I make a rectangle, you can see that it goes a little bit over. So this area here is as h gets really close to x, this green line comes closer and closer to the blue dotted line, and the area that I'm going to have in here, so let me just show you this in a different color. So the area that I'm going to have here, so the area here is actually going to be closer and closer to a rectangle that has height f of x and width h, some very small value in h. So height f of x and the width is h. So this, I can say, this here is actually very close to the value when h goes small. So this is actually very close to the value h times f of x. Okay, so as we bring h closer and closer here, and even closer than that, then I will get some rectangle here, and the area for that rectangle would be very close to f of x times that very small value h. So now, for looking at this, if I was to divide both sides by h, then I'm going to get this. And then if I was to take the limit as h tends to 0, then I can say that will actually equal to f of x. So I'm going to say a x plus h, take away a of x, divide that by h, okay? And now I've got f of x on this side because I've divided by the h on that side. And then I'm going to say I'm going to take the limit as h tends to 0. And then I know that when I said as h tends to 0, the value here is going to be very close to f of x. So this is actually going to be equal to f of x. Now, this is actually very interesting because this, remember, is the differential of a of x. So let's write that down. So let's say this is actually a dash x equals f of x. Now, we must remember that the function a of x was about the area under the graph. And here what I have is the differential of f of x, the differential of capital A of x is actually f of x. Now, so that means this, the antiderivative of f of x has to be capital A of x. So I know that the antiderivative of f of x I normally write with a capital F. Therefore, I can see that capital A of x is actually equal to capital F of x. And again, this is very interesting because what this does is this relates differentiation to the antiderivative and also to the integral here, which we said is the area under the curve. So what we can see is the integration is very close. And the integration was about the area under the curve, and differentiation is about the gradients. And we can see that they are very closely linked together because what we have is the antiderivative of lowercase f of x is actually the area function. And therefore, we can say that the area function is actually capital F of x. Here I will go over some examples of how to evaluate indefinite integrals. So we've just seen that integrating is the same as finding the antiderivative. Okay, so what we can do is we can just find the antiderivative of this, and it's indefinite integrals. What you'll notice is that there's no lower bound and upper bound, and we're looking for a general antiderivative or a general integral. We have to say plus c. Okay, so this would be, okay, so add 1 to the power. So add 1 to the power, make it x cubed and divided by 3. So this is going to be 2x cubed over 3. I need to add 1 to the power and divide it by that. So that's going to be dividing by 2. So take away 3x squared divided by 2. This here would be 5x plus 5x. And because I'm evaluating an indefinite integral without bounds, I need to say plus c here. Plus c. Next one. This one here, if I multiply this out, then I will get, we can say lots of things added together. or lots of functions added together, and that's easier to evaluate. So what we have to do here is first multiply it out, and then we'll evaluate the integral. So this integral is going to be 5x cubed take away 15x squared plus 20x take away 3x squared plus 9x and take away 12. Now I can evaluate this integral, but actually it's easier for me if I was to simplify some of these. So let's do that. So this integral is 5x cubed. It is take away 18x squared plus 29x and take away 12 with respect to x. So I'm integrating this with respect to x. That's what the dx is there for. So now I'm going to integrate this, or find the antiderivative. So add 1 to the power, make it x to the power of 4, and divide it by that. So we're going to get 5x to the power of 4 over 4. Here I'm going to add 1 to the power, make it 3, and divide it by 3. So it's going to be take away 18x cubed over 3. Then I'm going to have add 29x squared over 2, take away 12x. And because this is an indefinite integral, I have to say plus c, because I'm finding a general antiderivative or a general integral. Now I can see that this fraction here simplifies, so I'm going to simplify that one now. So we're going to have 5x to the power of 4 over 4, take away 6x cubed, plus 29x squared over 2, take away 12x, plus c. Now here are some practice questions for you to try. So you have to evaluate these indefinite integrals, and here they are.